All right, in this second part, we continue on logic design concepts, and we will get into basic gates. And we have already covered the number system, and we have discussed various ways of describing or representing numbers. Basic logic gates and structures, this is what we will be doing now. And in there, we will first talk about logic value system. Why logic value system? Well, so far we have only talked about zeros and ones, but then in real electronics, there is more than 0 and 1. There are voltages in between, there are non-driven voltages, there are conflicts that cause some voltage between the high and low, and therefore those also have to be represented. Even though Boolean logic does not support that, sorry, but for hardware description languages like Verilog or VHDL, if we were to represent circuits in the in the hardware description languages, those other values become important as well. So we talk about those, and then we talk about logic function representations and inverters, NAND gates, NOR gates, multiplexers, and the majority function. All right, so let's start with logic value system, and here I'm showing a table showing four values: 0, 1, Z, and X. Okay, let's take a very simple inverter and show the circuit diagram in CMOS. This is input A, this is supply, and this is the ground, and this becomes the output of the inverter. And if my A input is 0, then see what happens. If the A input is 0, okay, the lower transistor is off and the upper transistor is conducting, and therefore I have a path from my supply to my output, and therefore I call this a forcing 1. That means it's a real 1, it is driven 1, okay, which is this value over here, okay. On the other hand, if for example my A input is 1, the upper transistor will not be conducting, but the lower transistor will be conducting, and therefore I have a path from my inverter output down to ground, and then I have a driven 0. Okay, when we say driven 0, means there is a electric path from the output down to ground, and therefore it is a 0. But when it says driven, it's looking at it from the logical point of view, where a 0 from ground will be going and driving my output. So this is this situation right there, and this is giving me a 0. So the arrow I'm drawing here, which is from the output down to the ground, is showing the current flow. If I were to show the logical flow, it would be this way, okay, logical, okay, meaning a 0 is driving my output. All right, the two transistors have different delays. For example, when the input changes from 0 to 1, the upper transistor reacts slower than the NMOS transistor, which is the lower transistor. So there will be times that either none of the two transistors will be conducting. Okay, if none of the two transistors are conducting, let's, for example, look at this scenario. If let's try another inverter. Okay, this is another inverter, A input, W output, and let's say A is 0, and then later A changes to 1, so it's 0, and then it's changing to 1. Okay, when it's 0, the upper transistor is conducting, and the lower transistor is not conducting. But when it changes to 1, the lower transistor reacts quicker, so there will be a 0 coming here, whereas the upper transistor still, because of the 0 on the A input, still has a path to the output, and therefore momentarily, for a very little amount of time, both the upper transistor and the lower transistor will be driving. So what happens then? That's because of the different delays, of course. What happens is that my output that was originally 1, W was 1, for a short period of time will be some value driven by 0 and 1, and then it becomes 0. So this value here is neither a 0 nor a 1, it's a conflict. Okay, and therefore, how do we represent that? Well, I represent that by X or the conflict here. Okay, the opposite of it is also true, and in that situation, let's use still a different color, and I'm going to use orange, and let's say my A is 1. And the A is 1, this is conducting, putting a 0 on the output, and therefore my output is 0. And later on it changes to 0. When this is a 1, this one is not conducting, right? Now, my input from 1 to 0 changes, and therefore the lower transistor will become open. When it becomes open, it means that it's not driving a 0 into the output. Okay, and then what happens is that the 0 will cause the upper one to eventually conduct, but then again, because the PMOS transistor is slower than the NMOS, it takes longer for the PMOS transistor to react, and therefore there will be a period of time that neither the NMOS transistor nor the PMOS transistor are conducting, and therefore there will be a period of time that the output, we don't know, is not driven by neither one of those transistors, and therefore that's a Z value. All right. So to represent these situations, I need something beyond just 0 and 1. I need something like 0, a 1, a Z, and an X. Another example for these values would be like, for example, if you have a transistor here and another transistor here, and you're talking about this line driven by these two transistors. Let's say this is my output. Okay, if let's say you have a 1 here, let's say you have a 0 here, and now let's say the two transistors are we can do up to 4 values, right? If the two transistors are 0, 0, none of the two transistors will be conducting, and therefore the value on W is neither a 0 nor a 1, and it's not driven at all, and therefore the value on W becomes a Z. Okay, now if you take the 0, 1 situation, then let's do the 0, 1 situation, and I'm going to be using the same color here. Okay, this is a 0, this is a 1. If I'm using a 0, 1 situation, then the upper transistor is not conducting, the lower transistor will be conducting, forcing a 0 into the output, and therefore my output becomes a 0. All right, let's look at this situation now, where I have a 1 here and a 0 here. Okay, the lower transistor will not be conducting, and therefore nothing will be here, but the upper transistor will be conducting, pushing a 1 into this, and therefore my output becomes a 1. And finally, let's say that I have this very unpleasant situation where this is a 1, this is a 1. The upper transistor puts or pushes a 1 into the output. The lower transistor pushes a 0 into the output. How do I represent that? Well, I represent that with an X, which means a conflict or something bad is happening. And therefore, to be able to represent all these situations, we use the 4-value system, which includes a 0, a 1, an X, and a Z. Okay, so let's go on to the basic gates, and in some gates I'll be showing that we use that. Here I have an inverter, and the inverter is built with a PMOS and an NMOS transistor. And inside an inverter, like I said, there is a pull-up transistor like this one. There's a pull-down transistor like this one over here. And the output will be the complement of the input. And the way we can represent this, obviously this is not good. Input of 0 gives an output of 1. Input of 1 gives an output of 0. And these are two ways we can draw an inverter. These are ways we can write an inverter. This is the Boolean form. This is the text form. You put a prime when you don't want to draw a bar on top of things. And this middle way is the Verilog way. And you use a tilde. In VHDL, you write a nut. And just to be complete, let's also show the transistor circuit. This is A, this is W. And okay. I guess I pushed something which I shouldn't have. Let's do 23. Okay. All right. This is a NAND gate, and the transistor circuit for a NAND gate is this. This is A input. This is B input. This is the supply, WB. Okay, and that's a NAND gate. The lower part conducts if both A and B are 1, and then when it conducts, the output is 0. And the output is 1 when you don't have a 1, 1 on the output. And this is the Verilog format. This is the way you write it, part of text, and this is the bar for the writing logic expressions. This is a NOR gate, and again, to be complete, let's do the transistor circuit for the NOR gate. And this is let's okay, this is the A input, this is the B input, This is the W output. And again, the output is 1 when both inputs are 0. Otherwise, the output is 0. And this is the way you write it in Verilog with the vertical bar. In VHDL, you write like A, NOR, B. Okay? And so this is the symbol. Something I did not mention about the inverter, or actually about these bubbles, is that you can put the bubble anywhere you want. So when you draw an inverter, this is an inverter. This is also an inverter. Okay? For the AND gate, this is also okay. This is also a NAND gate. Okay, so instead of putting a bubble on the output, you can put 2 bubbles on the input. NOR gate, this is also a NOR gate. Okay, it's not a NOR gate, it is a NOR function. Okay, so whether you draw it like this or you draw it like this is the same thing. And obviously, AND and NOR are just the non-complement of these gates, and this is A and B. This is A and B, writing it in Verilog, and the truth table for the AND is what I'm showing here. The truth table for the OR is what I'm showing over here. And when you're doing if you want to do a circuit, if you want to do CMOS circuit, the only way you can do an ANDing, if you want to do the complete circuit for it, the PMOS and the NMOS, the only way you can do it is to have an AND gate and then have an inverter in front of it. So for example, if you want to do an AND function, this is what becomes for the AND. Okay, so this is input A, this is input B, and then this has to go into the inverter, this output, and this becomes your W output for ANDing. And then ORing, you do an NOR, and you do an inverter in front of it. For the NAND, this is how it's usually drawn. So the 2 bubbles next to each other indicate that they cancel out, and then the whole thing is NAND. An AND. The whole thing here is AND. XOR gate, you can build an XOR gate with NAND gates, with NOR gates, with AND gates, OR gates, and inverters, and the function is what I'm showing over here. XOR means the output becomes a 1 if only either one of the inputs is a 1. So with OR, you get a 1 over here. Okay, but then with, let's look at the previous one, with the OR, you get 1s all the way for all these 3 outputs. But with an XOR, you only get 1 when either one of the inputs is 1. Another way of looking at the XOR is if you have an XOR with 5 inputs, let's say, for example, the output is 1 when the number of 1s on the inputs is odd. Another way of looking at XOR is if this input is 1, the output becomes the complement of the other input. And if this input is 0, the output becomes the same as the input. And the way it works is 0, 0 gives you a 0, 0, 1 gives you a 1. That means they are different. if 1 0 you get a 1 and 1 1 you get a 0. And something else I also need to say about an XOR, the output is 1 if the two inputs are different, a 0, a 1, a 1, a 0. Okay, or if the two inputs are equal, the output becomes a 0. An XNOR is like a 1-bit comparator. The output becomes a 1 when A and B are equal. 1 if A equal B. All right. This is the logical symbol for it. This is the Verilog symbol for it. The VHDL symbol would be like A XOR B. And this is the truth table for it. Okay, so XOR, several ways of using it. It's a 1-bit comparator. It's an odd generator. It is also a controlled inverter. Okay? W is A if B is 1. W is A bar if B is 1. Otherwise, W is A. If B is 0, then just send the A through, which is a controlled inverter.